Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly let me know in the chats. Quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Yes, welcome back people, welcome back. Yes, today is going to be the last session of the chapter Redox reactions and we shall be completing it today, right? And my dear students, let me tell you, today is going to be one of the most important topics of the chapter Redox reactions, from which question frequently comes when it comes to your NEET examination, right? So give me some green signal from the chats if all of you can hear me, if I'm perfectly audible, visible. Right? What would be the next chapter? Well, there is one session pending from the chapter Atomic Structure, right? I've already taken part 1 of Atomic Structure, right, which I posted like a week or 2 weeks back. I think I'll plan part 2 of Atomic Structure, which is going to be the last session of Atomic Structure. Okay? I'll let you know in the Telegram. I will let you know in the Telegram. Perfect. I'll let you know about that. All right, so I think I'm perfectly audible and visible. So without wasting a lot of our time, let's get going. Let's get started. And before starting this particular session, the ones who have not liked the session yet, do like the session, right? Do share this particular video with everyone whosoever is preparing for NEET 2025 or even 2026. This particular session will be for everyone. And at the same time, the ones who have not subscribed to the channel yet, I would want you guys to subscribe to the channel as well. Well, it is, someone is writing, it's someone's birthday. Whose birthday is it? Payal. Happy birthday, Payal. God bless you. Happy birthday. Happy birthday. See guys, again I'm repeating the same thing. The ones who are not done with Atomic Structure Part 1, okay, do that tomorrow. You can search it on this particular channel, Atomic Structure Part 1 by Wasim sir. That session duration was almost like 6 to 7 hours, right? So I would want you guys to complete that first, then come to Atomic Structure Part 2, which I'll schedule on Monday. No, I'm not in Chennai right now. I'm in Srinagar. I'm in Srinagar, J&K. Who told you I'm in Chennai? No, not now. I was there last month. All right, guys. So let's get going then. Let's get started. And let me first of all tell you what exactly we are going to cover in the today's session. As you all must be knowing, today we are going to complete this particular chapter. And the things which we are going to discuss today, what are those things exactly? My dear students, the first topic of the today's session will be balancing of redox reactions. And once we are done with balancing of redox reactions, then we'll discuss a term called as normality. And once we are done with normality, then we shall be discussing about the redox titration as well. These are basically the 3 topics, the super important topics from which question frequently comes when it comes to your NEET exam, right? So these are the 3 topics which we shall be covering in the today's session. And with this, the chapter will be completely done and dusted. The session duration will be almost like 2 hours or maybe 2 hours, 30 minutes like that. 2.5 hours, perfect. And I would want you guys to be with me till the end, because again, I'm telling you the same thing. This session is going to be super important. Okay? Perfect, guys. So let's get going then. Let's get started. My dear students, the first thing with which I'm starting the today's session, what is that? I'm writing some common reactions. Some common reactions of KMnO4 and K2Cr2O7. Some common reactions of KMnO4 and K2Cr2O7. This is the first thing which we shall be discussing right now. I'm showing you some common reactions, some important reactions, which are basically shown by your KMnO4 and K2Cr2O7. And in which medium exactly I'm talking about? I'm talking about the acidic medium. Try to understand what exactly I'm going to say. My dear students, first of all, if you talk about your KMnO4, it is a strong oxidizing agent. KMnO4, it's a very strong oxidizing agent. And the first thing which you must remember from now onwards, which I have told you in the last session as well, KMnO4 in acidic medium, it gets converted into Mn di-positive. In acidic medium, the KMnO4, which is a strong oxidizing agent, it gets converted into what? It gets converted into Mn di-positive. Point number one. My dear students, if the KMnO4 gets converted into Mn di-positive in acidic medium, and if I ask you, what is the N factor of KMnO4 here in acidic medium? You should be in a position to tell me what exactly is the N factor of KMnO4 here in the acidic medium. My dear students, look carefully. The oxidation state of manganese over here is +7. The oxidation state of manganese here is +2. So +7 to +2, +7 to +2, what will be the change in the oxidation state? It's going to be final minus initial. The value comes out to be 5. 5 is the change for 1 atom of manganese, and I have got only 1 atom of manganese. So its N factor in acidic medium is 5, right? Now, this KMnO4, someone is asking, where do I get the notes? Notes you'll be getting in my Telegram right after the session, right? Which is Wasim Bhatt Chemistry Official. You can search it out, Wasim Bhatt Chemistry Official, okay? In that particular Telegram, once you join in, you'll be getting the notes of all the sessions which I take over here. So see guys, now this KMnO4, which is a very strong oxidizing agent, it shows certain reactions, some important reactions, which you need to remember from now onwards. The first one. Let me tell you this KMnO4, which I wrote over here. KMnO4 converts Fe di-positive into Fe tri-positive. In which medium? In acidic medium. The first thing which you'll remember. KMnO4 converts Fe di-positive into Fe tri-positive in acidic medium. This is the first thing which I would want you guys to remember. Number one. Number two. The same KMnO4, it converts I negative into I2. It converts I negative into I2. In which medium? Acidic medium. The same KMnO4, it converts Sn di-positive into Sn plus 4. In which medium? Again acidic medium. KMnO4 converts oxalate ion, C2O4 di-negative, into what? Into carbon dioxide. In which medium? Again acidic medium. The same KMnO4, it converts H2O2 into O2. In which medium? Again acidic medium. The same KMnO4, it converts H2S into sulfur. In which medium? Again in acidic medium. The same KMnO4, it converts SO2 into SO4 di-negative. In which medium? Again in acidic medium. These are few things which I would want you guys to remember right now. Okay? KMnO4 in acidic medium. It converts Fe di-positive into tri-positive, I negative into I2, Sn di-positive into Sn plus 4, oxalate into carbon dioxide, H2O2 into O2, H2S into sulfur, SO2 into SO4 di-negative. These are few things which I would want you guys to remember right now. And once you remember these things, then you can easily write the reactions as well. Now, how exactly? Try to understand. See guys, since I'm talking about KMnO4, as I told you, KMnO4, it converts Fe di-positive. In which medium? In acidic medium. Into what? It converts it into Fe tri-positive. And itself in acidic medium gets converted into Mn di-positive. And with this, you'll be adding water as well. This is a complete reaction. This is the complete reaction. Okay, this is the complete reaction. Similarly, if you look at the second reaction, the same KMnO4 converts I negative. In which medium? In acidic medium. Into what? Into I2. Itself gets converted into Mn di positive. And with this, you'll be writing water as well. This is one more complete reaction which you have mentioned over here. And my dear students, in the similar way, you can write all the other reactions as well. For example, the third one, the same KMnO4 converts Sn di positive. In which medium? In acidic medium. Into what? Sn plus 4. Itself gets converted into Mn di positive. And with this, you'll be writing water as well. So this is your one more reaction. Similarly, the next one, KMnO4 converts oxalate ion. It converts oxalate ion. In which medium? Acidic medium. Into what? Into carbon dioxide. And itself gets converted into Mn di positive. And with this, you'll be writing water as well. Similarly, you can write the rest of the reactions on your own. Right? Is it clear till here? These are few reactions, my dear students, which you need to remember. And you can only write these reactions if you exactly know what KMnO4 does. Right? And I've already told you what this KMnO4 does. It converts Fe di positive into Fe tri positive, I negative into I2, and so on. Okay? Perfect. These are some important reactions which are shown by your KMnO4. My dear students, similar reactions are shown by your K2Cr2O7 as well. Similar reactions are shown by your K2Cr2O7 as well. Let me tell you, K2Cr2O7, it's again a strong oxidizing agent. It's again a strong oxidizing agent. And in acidic medium, let me tell you, in acidic medium, it gets converted into Cr tri positive. In acidic medium, it gets converted into Cr tri positive. Now, the first thing which I'm asking you over here, what do you think is the N factor of K2Cr2O7 over here in this reaction? What exactly? I've told you in the last session how to calculate the N factor. We have discussed the N factor calculation in detail in the last session. I hope you remember. I hope you remember. Yeah? Tell me quickly. Tell me quickly, people. See, guys, the oxidation state of chromium here is plus 6. The oxidation state of chromium here is plus 3. Plus 6 to plus 3. What is the change? What is the change in oxidation state? It is just going to be final oxidation state minus the initial oxidation state. The value comes out to be 3. 3 is the change in the oxidation state for one chromium atom. And over here I have 2. So 3 2s comes out to be 6. So its N factor here is 6. As simple as that. Okay. Now, whatever reactions your KMnO4 was showing in acidic medium, similar reactions this K2Cr2O7 also is going to show. Now, what exactly? Let me write them again. The first one. K2Cr2O7 converts Fe di positive into Fe tri positive. In which medium? Acidic medium. It converts I negative into I2. In which medium? Again acidic medium. It converts Sn di positive into what? Into Sn plus 4. In which medium? Again acidic medium. The same K2Cr2O7 converts oxalate ion into carbon dioxide. The same KMnO4 converts H2O2 into O2. In which medium? All these are happening in acidic medium. Similarly, the same KMnO4, it converts H2S into sulfur. And in the similar way, the same KMnO4 converts SO2 into SO4 di-negative. In which medium? Again in acidic medium. Now, my dear students, you should be in a position to write all these reactions on your own. You should be in a position to write all these complete reactions on your own. Have a look. Since right now I'm talking about your K2Cr2O7. As I told you, K2Cr2O7 converts Fe di positive. In which medium? Acidic medium. Into what? Into Fe tri positive. Itself gets converted into Cr tri positive. And with this, you'll be writing water as well. So there's a complete reaction now. It's a complete reaction now. My dear students, similarly, let's try to write one more reaction. The same K2Cr2O7, it converts I negative. In which medium? Acidic medium. Into what? Into I2. itself gets converted into Cr tri-positive, and with this you'll be writing water as well. You can write any of these reactions over here which are mentioned. For example, I want to write this reaction. I'm right now talking about your K2Cr2O7. K2Cr2O7 converts what? H2O2. It converts H2O2. In which medium? Acidic medium. Into what? Into O2. Itself gets converted into Cr tri-positive, and with this you'll be writing water as well. So this is the reaction. And similarly, you can write all these reactions on your own. Right? You can mention all these reactions, you can write all these reactions on your own. Because you exactly know it converts what into what. You know it already. Am I clear till here? Am I clear till here? Let me know once in the chats if you can write all these reactions on your own now. Say it in the chats quickly. If you can write all these reactions on your own, let me know once in the chats quickly. Quickly, people. Quickly. Everyone. Everyone, quickly. Yeah? Let me know once the chats quickly. Yes or no? Perfect, guys. Perfect. Now, I'm moving on to our actual topic, which we have to discuss. What is that? That is balancing of redox reactions. Balancing of redox reactions. Balancing of redox reactions. My dear students, let me first of all tell you there are two methods. There are basically two methods. There are two methods which can be used to balance a redox reaction. First method is going to be your oxidation number method, which is the easiest. Oxidation number method. And the second one is going to be your ion-electron method. Your ion-electron method. Oxidation number method and ion-electron method. First of all, we shall be discussing about the oxidation number method, and later on, we shall be discussing about the ion-electron method as well. Okay? Now, my dear students, this oxidation number method, we shall be discussing in two parts. First of all, we shall be discussing about the balancing of redox reactions with the help of oxidation number method in acidic medium. Then we'll see the balancing of redox reactions with the help of oxidation number method in which medium? In basic medium, right? Similarly, ion-electron method also we are going to study in two mediums. First, we shall be discussing about ion-electron method in acidic medium and ion-electron method in basic medium, right? So all this I'm going to teach you in detail. All this I'm going to teach you in detail. And right now, let's get started with the balancing of redox reactions with the help of oxidation number method in acidic medium. Okay, let me mark the heading over here as oxidation number method. Oxidation number method in which medium exactly? In acidic medium. Oxidation number method in acidic medium. In acidic medium. Okay. See guys, have a look properly what exactly I'm going to do now. Understand step by step what exactly I'm going to do. For example, I'm taking the reaction over here. Let's say the reaction is your MnO4 negative plus Fe di positive. Let's say it gives Mn di positive plus Fe tri positive. Let's say this reaction I need to balance in acidic medium with the help of oxidation number method. How exactly am I going to do it? Understand, people. The first thing, what exactly I'll be doing, I will be calculating the n factors of these reactants. I'll be calculating n factors of these reactants over here. See, we have got MnO4 negative. What is its n factor? N factor here is 5 because it's participating in acidic medium. What is the n factor of Fe di positive? Plus 2 to plus 3. What is the change in oxidation state? 1. 1 is the change for one atom. I've got only 1. So its n factor is 1. So I calculated the n factors of reactants. My dear students, once you get the n factors of reactants, you just have to crisscross these n factors. What does that mean? That means take this 1, make it as the stoichiometric coefficient here. Take this 5, make the stoichiometric coefficient here. So my first step was to calculate the n factors. After calculating the n factors, just crisscross the n factors. Just crisscross the n factors. Okay? Now, let me write it step by step over here. First of all, I calculated what? I calculated the n factors of reactants. My second step was crisscross the n factors. Crisscross the n factors. Now, after crisscrossing the n factors, balance all the atoms. Balance all the atoms except hydrogen and oxygen. Balance all the atoms except hydrogen and oxygen. Now try to balance it. Except hydrogen, oxygen. We have got 1 manganese here, so make it 1 manganese here. Right? We have got 5 iron here, so make it 5 iron here. Balanced all the atoms except hydrogen, oxygen. Now, my dear students, after doing this part, now you are going to balance oxygen atoms with the help of water molecules. And then you are going to balance hydrogen atoms with the help of H positives. That's it. So what is the turn now? We have to balance the oxygen atoms with the help of water molecules. How exactly? Understand. If I ask you how many oxygen atoms do you see on the left side? I can see 4 oxygen atoms on the left side. Is there any oxygen atom on the right side? There is no oxygen atom on the right side. So which side is oxygen deficient? Which side is oxygen deficient? I'll say right side is oxygen deficient. How many oxygen deficiencies are there? See, on this side 4, on this side none. That means this side is oxygen deficient. If this side is oxygen deficient, what I'll be doing? What I'll be doing? First of all, if I ask you how many oxygen deficiencies are there are 4 oxygen deficiencies on this side. And oxygen deficiency is compensated by adding water molecules. So just do one thing, add 4 water molecules on this side. Oxygen is balanced with the help of water molecules, right? Perfect. So oxygen is balanced. Now after oxygen, my turn is for hydrogen. Balance hydrogen with the help of H positives. So how many hydrogens on left side? No hydrogen. How many hydrogen on right side? 4 to the 8. 8 hydrogen atoms on right side. So which side is hydrogen deficient? This side, left side is hydrogen deficient. How many hydrogen deficiency? 8. Number of hydrogen deficiency means add 8 H positives on this side. Now this reaction is balanced. You need not to check it. It's a balanced chemical equation now. Is it clear? Is it clear, people? Did you understand? Did you understand this? Quickly. This is how you use the oxidation number method in acidic medium to balance a particular reaction. Let me take one more example so that it becomes clear to you properly. See guys, let me take one more reaction. Let me take one more reaction. For example, you have got Cr2O7 dinegative plus Cr2O7 dinegative plus oxalate ion C2O4 dinegative. Let's say it gives Cr tripositive plus carbon dioxide. Let's try to balance this particular reaction in acidic medium with the help of oxidation number method. See, again the same procedure. What I'll be following. What exactly? First of all, calculate the n factor of reactants. Calculate the n factor of reactants. How do you calculate n factor of reactants? See, oxidation state of chromium here is plus 6. Here it is plus 3. Plus 6 to plus 3. Change is 3. 3 is the change for 1 atom. I have 2. So 3 2s are 6. Its n factor is 6. Carbon. Here is in plus 3 oxidation state. Here it is in plus 4 oxidation state. So plus 3 to plus 4. What is the change? 1. 1 is the change for 1 atom. I have 2. Right? So its n factor is 2. So first thing, what I exactly did, I calculated the n factors over here. I calculated the n factors of reactants. Now, after calculating n factors of reactants, what exactly am I supposed to do? I'm supposed to crisscross these n factors. So take this 2, make it the stoichiometric coefficient here. Take this 6, make it the stoichiometric coefficient here. Now, after crisscrossing, balance all the atoms except hydrogen oxygen. So 4 chromium here, so make it 4 chromium. 6 2s are 12 carbon here, make it 12 carbon. So we have balanced all the atoms except hydrogen oxygen. Now it is the turn for oxygen atoms. How many oxygen atoms do you see on left side? 7 2s are 14 here. 6 4s are 24. 24 here. So in total on left side, you have got 38 oxygen atoms. On right side, 12 2s are 24. 12 2s are 24. On right side, you have got 24 oxygen atoms. So which side is oxygen deficient? Right side is oxygen deficient. How many oxygen deficiencies are there? 14 oxygen deficiencies are there. So add 14 water molecules here. With this, your oxygen is balanced. Now, after balancing the oxygen, it is the time to balance hydrogen. So how many hydrogens do you see on right side? 14 to the 28. How many hydrogens are there on left side? No hydrogen. So this side is hydrogen deficient. And how many hydrogen deficiencies? 28. So add 28 H positives on this side. This reaction is balanced now. No need to check. Is that clear? Is it clear? Let me know once in the chats quick. Is it clear, people? Will you be able to use this particular method from now onwards easily? Yeah? Perfect. One homework I'll be giving you here, and you'll be trying it afterwards. One homework question. Procedure is completely same. Let's say the reaction is Cr2O7 dinegative plus Sn di positive. It gives Cr tri positive plus Sn plus 4. You are going to balance this reaction on your own afterwards, not now. Afterwards, once the session ends. Okay? Perfect. Now, people. So this was your oxidation number method in acidic medium. Now let's talk about the same oxidation number method in basic medium. Oxidation number method in basic medium. In basic medium. So what are the steps exactly over here? The steps are almost similar. There are few chains. That's it. Steps are almost similar, but there are few chains. How can you find the reaction is in acidic or basic medium? It will be mentioned in the question. It will be mentioned there whether the reaction is taking place in acidic or basic medium. See guys, first of all, let me write the steps which are to be used over here. The first step is same. That is, calculate the n factors of reactants. N factors of reactants. Once you are done with the calculation of n factors of reactants, what you need to do? Crisscross. Crisscross these n factors. After that, balance all the atoms. Balance all the atoms except hydrogen oxygen. Except hydrogen and oxygen. After that, in acidic medium, we used to balance oxygen. Now here we are not going to balance oxygen first. Here we are going to balance negative charge first with the help of OH negatives. With the help of OH negatives. Then later on, you'll be balancing oxygen with the help of water molecules. That's it. This is the procedure. This is the procedure, people. Try to understand what exactly I'm going to do. Let me take some reaction so that I could balance that. For example, I've got the reaction like this. Cl2 plus IO3 negative. It gives Cl negative plus IO4 negative. Let's say this is one reaction. Let's try to balance this particular reaction in basic medium with the help of oxidation number method. So what is my first step? I need to calculate the n factors of the reactants over here. Okay, how do you exactly calculate the n factors now? You know it already. Oxidation state of chlorine is 0 here. It is -1 here. 0 to -1. What is the change? 1. 1 is the change for one atom. I have 2. So its n factor is 2. Okay. Iodine here is in +5 oxidation state. Here the same iodine is in +7. +5 to +7. +5 to +7. Change. Change is 2. 2 is the change for one atom of iodine. I've got only 1. So its n factor is 2. So what did you calculate over here? We got the n factors of reactants. We got the n factors of reactants. Once you get the n factors of reactants, you are supposed to crisscross them. So 2, make it as a coefficient here. This 2, make it as the coefficient here. Done with this? Yes, done with this part. Now, we are done till here. Balance all the atoms except hydrogen oxygen. Balance all the atoms except hydrogen and oxygen. My dear students, you have got 4 chlorine atoms on this side. Make it 4 chlorine. You have got 2 iodine atoms on this side. Make it 2 iodine. So you balanced all the atoms except hydrogen oxygen. So we are done till here. Now is the time for the negative charge. Negative charge is balanced with the help of OH negatives. Try to understand how. Is there any charge on this chlorine? No. Do you see any charge here? Yes, we can see the charge here. I'll say one IO3 molecule carries charge -1. So 2 IO3 molecules will carry the charge -2. So on left side, there is charge -2. On left side, the total charge is -2. Look at the right side. On 1 chlorine, charge is -1. On 4 chlorine, charge will be -4. On 1 IO4, charge is -1. On 2 IO4, charge is -2. So -4 -2 makes it -6. So left side, -2 charge. Right side, -6 charge. Which side is negative charge deficient? Which side is negative charge deficient? Left side is negative charge deficient. How many negative charge deficiencies are there? I'd say 4 negative charge deficiencies are there, right? So what you need to do, negative charge deficiency is compensated by OH negatives. So add 4 OH negatives on this side. Add 4 OH negatives on the side which is negative charge deficient, right? So we are done till here. Now is the turn for oxygen atoms, right? So balance oxygen now. So how many oxygen on left side? 3 2s are 6, 6 4 10. 10 oxygen on left side. 2 4s are 8. 8 oxygen on right side. So which side is oxygen deficient? Right side. How many oxygen deficiencies are there? 2, right? Number of oxygen deficiencies means, so add 2 water molecules here. Then now the reaction is balanced. Now it's a balanced chemical equation. I believe it's clear. It's a balanced chemical equation now. Okay, it's a balanced chemical equation now. I hope I'm clear with this. Let's take one more example so that it becomes properly clear. Let's say you've got the reaction like this. Let's say you've got MnO4 negative plus Br negative gives MnO2 plus BrO3 negative. You need to balance this reaction, for example, in basic medium, right? Same steps, my dear students, you are going to follow. Same steps, one by one. Calculate the N factors, first of all, of the reactants. Calculate the N factors of the reactants. What is the N factor of this MnO4 negative here? Quickly. Quickly, people. Quickly. This is something which you should be answering, right? MnO4 negative, what is its N factor? See guys, if you look at its oxidation state of manganese here is +7, and the oxidation state of manganese is +4. So +7 to +4, change is 3. 3 is the change for 1 atom of manganese. I've got only 1 atom. So its N factor is 3. Simple, right? Very simple. Similarly, bromine from -1 to +5. -1 to +5, what is the change in the oxidation state? Final minus initial. So 5 minus -1 comes out to be 6. 6 is the change for 1 atom. And I've got only 1 atom. So its N factor is 6. So I got the N factors of both. I got the N factors of both. Right? My dear students, since you got the N factors of both, now what is the next step? The next step is to crisscross these N factors. So make this 6 as the stoichiometric coefficient here. Take this 3 as the stoichiometric coefficient here. Done? So once we are done with crisscrossing, balance all the atoms except hydrogen and oxygen. Balance all the atoms except hydrogen and oxygen. So 6 manganese on this side, make it 6. 3 bromine on this side, make it 3. Right? So we are done till here. Now we have to balance the negative charge. And negative charge is balanced with the help of OH negatives. So if I ask you, is there any charge here? Yes. How much? -1. So on 1 MnO4, the charge is -1. On 6, there will be -6. 1 Br carry charge -1, 3 will carry -3. So -6 -3 carries -9, right? There is no charge here. Yes, there is charge here. 1 BrO3 molecule carries -1, so 3 will carry -3, right? 3 will carry -3. So if you look carefully now, -9, -3. Which side is negative charge deficient? Right side is negative charge deficient. How many negative charge deficiencies are there? There are 6 negative charge deficiencies. So add 6 OH negatives on this side. Add 6 OH negatives on this side, right? Add 6 OH negatives on this side. Now balance oxygen. Balance oxygen now. Balance the oxygen atoms now. So first of all, 6 4s are 24. 24 oxygen on this side. 6 2s are 12. 3 3s are 9. And 6. Right? So this is 21. 21 plus 6 makes it 27. So 27 oxygen on this side. 24 oxygen atoms on this side. Right? Which side is oxygen deficient now? Left side is oxygen deficient. How many oxygen deficiencies? 3 oxygen deficiencies. If there are 3 oxygen deficiencies, so add 3 water molecules on this side now. Add 3 water molecules on the side which is negative charge deficient. Right? Perfect. check hydrogen would be automatically balanced. 3 2s are 6, and these are 6 hydrogens on this side. Look, if everything is balanced. Look, if everything is balanced. Check it out quickly. Check it out quickly, guys. All the things clear. See, manganese 6, manganese 6. 3 bromine, 3 bromine, right? How many oxygen? 6 for 24, 24 plus 3, 27. 6 to 12. 12 plus 9 is 21. 21 plus 6 is 27. So 27 oxygen on the other side too. And what after that? Hydrogen. 6 hydrogen, 6 hydrogen. Check the charge. Minus 6. Minus 6 minus 3 is minus 9. So this will be minus 3. Minus 6 comes out to be minus 9. Perfect. All right. Someone has come in the chats. Some Muzaka, Fatima. Wrong. Yeah, maybe you're right. Maybe you are right. Yes. All clear, guys? All clear, all clear? So I hope from now onwards, you will be able to use the oxidation number method either in acidic medium or in basic medium, right? You should be able to do that. You should be able to do that. Perfect. Perfect, guys. All right. So this was your balancing of redox reactions with the help of oxidation number method. In which medium? In basic medium. Now we are done with 2 parts. We are done with this one. We are done with this one. Now it is the time for ion-electron method in acidic and basic medium. Now let's try to understand this ion-electron method as well. Okay? Have a look. Have a look. So I'm marking the heading here as ion-electron method. Ion-electron method in acidic medium. This is also important. Ion-electron method in acidic medium. Over here, with the help of this particular method, you will understand, you will learn one more method of calculating the n factors. Okay? From this particular method, you will understand one more method. You will learn one more method of calculation of n factor. Now try to understand. There are few spammers in the chats. I need to block few. Perfect. Yeah, now it's fine. All right, people. So let's exactly get to know the ion-electron method in the acidic medium. Let me take certain examples so that you'll understand it properly. For example, I'm taking the reaction over here as, let's say I'm taking the same reaction, MnO4 negative, which we already balanced with the help of oxidation number method, plus Fe di positive. It gives Mn di positive plus Fe tri positive. See, this was one reaction which we already balanced with the help of oxidation number method, right? Now, the same reaction we are going to balance with the help of ion-electron method. Understand? Because there is something important which I'm going to tell you now. See, guys, over here, what are the steps first of all? What are the steps? The first step is to calculate the oxidation state of all the atoms. Calculate oxidation state of all the elements. This is the first step. Calculate oxidation state of all the elements. Let me calculate the oxidation state of all the elements. This is plus 7 and this is plus 2. This is also plus 2 and this is plus 3. I've calculated oxidation state of all the atoms, right? Number 1. Number 2, the second step. Second step is break this reaction into 2 parts. Break this reaction into 2 parts. Break into 2 parts. Break the reaction into 2 parts. One will be called as oxidation half reaction and other one will be called as reduction half reaction. We are supposed to break this particular reaction into two parts. One I'll be calling as oxidation half reaction, and another one I'll be calling as a reduction half reaction. Okay, how exactly? Understand. See guys, manganese +7 to +2. +7 to +2 means decrease in the oxidation state. Decrease in the oxidation state means reduction. So this MnO4 negative is undergoing reduction, right? +2 to +3. +2 to +3. Increase in the oxidation state means oxidation. So I got to know which substance is undergoing reduction and which substance is undergoing oxidation. I got to know that. A reduction involves what? A reduction involves gain of electrons. A reduction involves gain of electrons. And oxidation involves the loss of electrons. So I got to know this MnO4 negative will be gaining some electrons and getting converted into what? And will be getting converted into Mn di positive. Similarly, Fe di positive will be losing some electrons and will be getting converted into Fe tri positive. This is something which I got to know till now. Now, my dear students, this main reaction, I'm going to divide it into two parts. One is going to be your oxidation half reaction. One is going to be your reduction half reaction. I'm going to break it into two parts. Oxidation half reaction, reduction half reaction. Now, which species among these two is undergoing oxidation? Fe di positive is undergoing oxidation. And it's getting converted into Fe tri positive. So, your Fe di positive is undergoing oxidation and finally it's getting converted into Fe tri positive. Now the point is, when this Fe di positive will be getting converted into Fe tri positive, it will be losing electrons. Fe di positive will be losing some electrons and then it will be getting converted into Fe tri positive. Now the point is, how many electrons it will be losing? How many electrons it will be losing? +2 to +3. +2 to +3. What is the change in the oxidation state? 1. Right? So this Fe di positive will be losing 1 electron and then it will be getting converted into Fe tri positive. Okay? Right? So this is my oxidation half reaction. Now talk about the reduction half reaction. Which species is undergoing reduction? MnO4 negative. It is undergoing reduction and the one that undergoes reduction gains electrons. So MnO4 negative will be gaining certain electrons and then will be getting converted into Mn di positive. I would say MnO4 negative will be gaining some electrons and finally will be getting converted into Mn di positive. Now the point is, how many electrons it will be gaining? +7 to +2. What is the change in oxidation state? Final minus initial. The value comes out to be 5, right? So it will be gaining 5 electrons here. Perfect, right? Now, my dear students, try to understand one thing very properly. I got oxidation half reaction, I got reduction half reaction. Now, in these oxidation half and reduction half reactions, balance all the atoms except hydrogen oxygen. Balance all atoms except what? Except hydrogen and oxygen. Balance all the atoms here only. And in oxidation half reaction, there is 1 iron here, 1 iron here, balanced. In reduction half reaction, 1 manganese here, 1 manganese here, balanced, right? And once we are done with this, now is the time to balance the electrons. Now is the time to balance the electrons. How exactly you guys are going to balance the electrons? See, in this reaction, there is 1 electron. In this reaction, there are 5 electrons. I need to make these electrons equal. I need to balance the electrons. How exactly I'll be balancing the electrons? I'll be multiplying this reaction by 5. And when I multiply this particular reaction by 5, it becomes 5 times. This becomes 5 times. Now this becomes 5 times. Now the electrons are balanced. So we have balanced the electrons. After balancing the electrons, add the reactions. Add the half reactions. After balancing the electrons, add the half reaction. Now, how exactly you'll be adding these half reactions? See, LHS side you'll be adding separately. RHS side you'll be adding separately. And when I'll be adding these two reactions, what you'll observe? You'll observe this 5 and this 5 will get cancelled out. So, on adding the left side part, it's going to be 5 times Fe di positive, 5 times Fe di positive plus what? Plus MnO4 negative. It gives what? It gives 5 times Fe tri positive plus what? Plus this Mn di positive. So you have added these two reactions. Left side part added separately, right side part added separately. Right? Right, people? Clear till here? Now, after doing this much, then it is the same. In acidic medium, what do? In acidic medium, we balance oxygen with the help of water molecules. Then we balance hydrogen with the help of H positives. That's what we are going to do here also. How many oxygen atoms on left side? 4 oxygen atoms. How many oxygen atoms on right side? No oxygen atoms. So right side is oxygen deficient, right? How many oxygen deficiencies? 4. So add 4 water molecules here. How many hydrogens here? 8. So add 8 H positives here. Now the reaction is balanced. It's a balanced chemical equation now. It's a balanced chemical equation. Now, my dear students, one important point. How many electrons got cancelled here? 5. So I'll say N value over here is 5. And this N represents what? N represents the number of moles of electrons exchanged in the net reaction. The number of moles of electrons exchanged in the net reaction. And one thing which I'm going to tell you now, that's important. Remember, one way of calculating N factor you already know. Calculate the change in the oxidation state, etc., etc. There is one more way of calculating the N factor. What is that? Let me tell you, N factor is always equal to number of moles of electrons exchanged divided by stoichiometric coefficient. Divided by stoichiometric coefficient. Now understand what exactly it means. What is the N value? N value here is 5. N value here is 5. For example, I want to calculate N factor of this Fe di positive. I want to calculate N factor of Fe di positive. What is the N value? N value is 5 divided by. What is its stoichiometric coefficient? 5. So 5 by 5 is 1. So its N factor is directly 1 here. Its N factor is directly 1. What about the N factor of MnO4 negative? What is the N value? That's 5. Divided by, what is its stoichiometric coefficient? 1. So 5 by 5 is 5. What about the N factor of Fe tri positive? N is 5 divided by, its stoichiometric coefficient is 5. That is 1. What is the N factor of this Mn di positive? 5 divided by 1 comes out to be 5. So this is one more way of calculating the N factors. Get the N value, divide them with the respective stoichiometric coefficients. You are done, you are sorted. Right? I'll take one more example with that every single thing will be clear. Right? I'll take one more example so that every single thing becomes clear to you. Let me take one more example, guys. Let me take one more example in acidic medium only. Okay, ion-electron method in acidic medium, one more example. Let's say we have got the reaction like this. Cr2O7 dinegative plus C2O4 dinegative. It gives Cr tripositive plus carbon dioxide. This is the reaction, for example, which we have to balance in acidic medium. Now, I hope you remember the steps. What are the steps? Oxidation state of all the atoms. Number 1. Number 2. Break the main reaction into 2 parts. Number 3. In oxidation and reduction of reaction, balance all the atoms. Next, balance the electrons. Next, add the half reactions. Next, balance oxygen with the help of water. Next, balance hydrogen with the help of H positives. Right? Let's follow all of these steps one by one. First thing, calculate the oxidation state of all the atoms. What is the oxidation state of chromium here? Plus 6. Oxidation state of carbon, plus 3. This chromium, plus 3. This carbon, plus 4. Now check which species is undergoing oxidation and which species is undergoing reduction. Plus 6 to plus 3, plus 6 to plus 3, decrease in the oxidation state. Decrease in the oxidation state means reduction. So this particular species is undergoing reduction. Cr2O7 dinegative is undergoing reduction. If it is undergoing reduction, it will be gaining electrons. It will be gaining electrons. Now, plus 3 to plus 4, plus 3 to plus 4, increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. So, this C2O4 dinegative is undergoing oxidation, and the one that undergoes oxidation, that loses electrons, right? That loses electrons. So, you got to know which one is going to gain electrons, which one is going to be losing electrons. You got to know about that. Now, what exactly we are going to do? We are going to break this main reaction into 2 parts. One is oxidation half reaction. One is your reduction half reaction. Now, among these 2 species, which one is undergoing oxidation? Oxalate ion. C2O4 dinegative is undergoing oxidation. And after oxidation, it's getting converted into what? It's going to get converted into carbon dioxide. Right? Now, oxidation involves loss of electrons. You know it. So, I'll say when oxalate, I'll say this oxalate, it will be losing electrons, then only it will be getting converted into carbon dioxide. This oxalate, it will be losing electrons, then only it will be getting converted into carbon dioxide. Okay. Now, how many electrons it will be losing? Before telling you that, in this reaction only, balance all the atoms except hydrogen, oxygen. See, 2 carbon, so 2 carbon. Now, the point is how many electrons this is losing. See, plus 3 to plus 4. What is the change? Plus 3 to plus 4. Change is 1. 1 is the change for one atom. How many do we have? We have 2. So, you'll write 2 electrons here. Simple. Done. Now go for the reduction of reaction. Which one is undergoing reduction? Cr2O7 dinegative. Cr2O7 dinegative is undergoing reduction, and finally it will be getting converted into what? It will be getting converted into Cr tripositive. After undergoing reduction, it will be getting converted into Cr tripositive. 2 chromium here, so make it 2, right? Now, since this is undergoing reduction, it will be gaining electrons. Now, the point is how many electrons this Cr2O7 dinegative will be gaining over here? See guys, plus 6 to plus 3. Plus 6 to plus 3. Change is 3. 3 is the change for 1 atom, I have 2. So 3 to are 6. 6 electrons it will be gaining. So we have written the oxidation of reaction as well as the reduction of reaction. Now people, if I ask you, are the electrons balanced here? You will say the electrons are not balanced. 2 and 6. What are we supposed to do? We are supposed to balance the electrons. So multiply this reaction by 3. Multiply this reaction by 3. When you multiply this reaction by 3, it becomes 3 times here. This becomes 3 2s are 6 times. And this becomes 3 2s are 6 electrons. Right? After balancing these electrons, I will be adding them. And when you add them, what will happen? The 6 electron gets cancelled out. What will be my net reaction? Net reaction is going to be 3 times C2O4 dinegative plus Cr2O7 dinegative. It gives what? It gives 6 times carbon dioxide plus 2 times Cr tripositive. This is the net reaction now. After reaching till here, my dear students, since the reaction is taking place in acidic medium, what do we balance now? We balance oxygen with the help of water molecules. So balance oxygen. 3, 4, 12. 12 plus 7 is 19. So 19 oxygen atoms on this side. 6 2s are 12. 12 oxygen atoms on this side. So which side is oxygen deficient? Right side. How many oxygen deficiency? 7 oxygen deficiency. 7 oxygen deficiency means 7 water molecules. Right? Now, after oxygen, it's the time for hydrogen. Look at hydrogen. 7 2s are 14. No hydrogen on this side. So left side is hydrogen deficient. How many hydrogen deficiencies? 14. So add 14 H positives on this side. Now this reaction is balanced. A balanced chemical equation. It is a balanced chemical equation, right? It's a balanced chemical equation, people. I believe it's clear. Yeah? I believe it's clear to everyone. It's a balanced chemical equation now. Since it's a balanced chemical equation, if I ask you how many electrons got cancelled out, you'll say 6. So the value of N here is 6. The value of N here is 6. If you got the value of N, tell me what will be the N factor of this particular species? It's going to be N divided by stoichiometric coefficient. So 6 divided by 3 comes out to be 2. 6 divided by 1 comes out to be 6. 6 divided by 6 comes out to be 1. 6 divided by 2 comes out to be 3. So these are all the N factors of these reactants and products which I calculated over here. I believe it's perfectly clear to everyone. If it is perfectly clear, let me know once in the chats quickly. Everybody. Everybody, people. Everyone. All clear? All clear till here? I want everyone to let me know in the chats. I'm looking at your chats only here. I am looking at your chats only here. Yeah? Perfect? Amazing, guys. So this was your ion-electron method in acidic medium. Can you let me know what will happen in ion-electron method in basic medium? Where will be the chains? The process is going to be similar. The process is going to be similar. There'll be one change. In acidic medium, we balance oxygen first, but in basic medium, we'll be balancing negative charge first with the help of OH negatives. Then we'll be balancing oxygen with the help of H2O molecules. Rest everything is clear. Rest everything is clear. Okay? Let me show one example here. Let me show one example. Ion-electron method in basic medium. And let me take one disproportionation reaction here. Let me take one disproportionation reaction in basic medium. Let me take one disproportionation reaction here in basic medium. And we are going to balance that with ion-electron method. Ion-electron method in basic medium. See guys, understand properly what exactly we are going to do. For example, you have got the reaction like this. Br2, it gives Br negative plus BrO3 negative. This is your reaction, for example. Okay, this is your reaction. This is your reaction, right? Perfect. My dear students, since this is your reaction, I'm assuming that this reaction is taking place in basic medium. This reaction is taking place in basic medium. Now balance this reaction with the help of ion-electron method. Balance this reaction with the help of ion-electron method. You should be in a position to do it. How exactly you're going to do? Calculate the oxidation state of all the species. 0, -1 and +5. 0 to -1, decrease in the oxidation state. So reduction. 0 to +5, increase in the oxidation state. So oxidation. So I got to know my oxidation half reaction and reduction half reaction. Oxidation half and reduction half. In oxidation reaction, what is happening? Br2 is getting converted into BrO3 negative. Br2 is getting converted into BrO3 negative. Since you have got 2 Br here, so make it 2 Br. Now, 0 to +5. 0 to +5. What is the change? Change is 5. 5 is the change for 1. I have 2. So 5 2s are 10. So it will be losing 10 electrons. Br2 will be losing 10 electrons. Then it will be getting converted into 2 times BrO3 negative. Point number 1. Right? Point number 1. Point number 2. Reduction. During reduction, what is happening? Br2 is getting converted into Br negative. Br2 is getting converted into what? Br negative. So if this is 2 Br, make it 2 Br. Now, since 0 to -1 means decrease, decrease means reduction, gain of electrons. So Br2 will be gaining some electrons, then getting converted into Br negative. Now how many? 0 to -1. What is the change? 1. 1 is the change for 1. I have 2. So it will be gaining 2 electrons here. Okay. Now if I ask you, are the electrons balanced? The electrons are not balanced yet. So it's high time to balance the electrons now. 10 electrons, 2 electrons. So what I'll be doing? I'll be multiplying this reaction by 5. When I multiply this reaction by 5, it becomes 5 here. This becomes 5 2s are 10. This becomes 5 2s are 10. Electrons are balanced. After balancing the electrons, add the reactions. Add the reactions. So 10 and 10 got cancelled. 5 Br2 plus Br2 makes it 6 Br2. Gives 2 times BrO3 negative plus what? Plus 10 times Br negative. Okay. Now, since this reaction is taking place in basic medium, and in basic medium, what do we balance first? We balance negative charge first. There is no negative charge on this side. On one molecule, the charge is -1. On 2, the charge is -2. On 1 Br, charge is -1. On 10, the charge is -10. So the value comes out to be -12. So on right side, the charge is -12, right? So this side is negative charge deficient. So add 12 OH negatives on this side. Now, it is the time for oxygen. It is the time for oxygen. How many oxygen here? 12. How many oxygen here? 3 2s are 6. So this side is oxygen deficient. How many oxygen deficiencies? 6 oxygen deficiencies. 6 oxygen deficient mean 6 water molecules. Now the reaction is balanced. It's a balanced chemical equation now. Since it is a balanced chemical equation, if I ask you what is the value of N here, N value is 10. Since you got the N value, if I ask you what is its N factor, so you will say 10 divided by 6, 10 by 6 is 5 by 3. 10 divided by 2 is 5. 10 by 10 is 1. So these are the respective N factors of these reactants and products which I was supposed to calculate. Right? I believe your balancing is absolutely clear over here. Yeah? Is it clear, people? Let me know once in the chats quick. Is it clear to everyone? Quickly, I want every one of you to let me know. Is it super clear to everyone? Is it super clear to everyone? I want everyone to let me know in the chats quick. I'm honestly, sir, give one example. I've given a lot of examples. Yes, once you are done with this session, after this session, our redox reaction chapter will be over. And after that, you will read your NCRT once. NCRT reading is must in this chapter. Once we are done with the lectures, then NCRT reading once. All right? Should I move on? Should I move on, people? All right, let's move on. Let's move on. Let me mark the heading here as concept of equivalence. Concept of equivalence. Concept of equivalence. My dear students, I'm going to give you few results. Okay, I'm going to give you few results. You guys are going to remember those results first of all. Okay, I'm going to give you few results directly. Just remember them directly. The first result. Number of gram equivalents. Number of gram equivalents of a substance. How do we calculate the number of gram equivalents of substance? And how do we calculate the number of milli equivalents of the substance? How do we calculate the number of milli equivalents of the substance? My dear students, the way you calculate moles of a substance, in the similar way you calculate gram equivalents of the substance, right? The way you calculate moles of some substance, in the similar way you calculate gram equivalents of the same substance. How exactly? Number of gram equivalents of the substance can be calculated as mass of the substance in grams divided by equivalent mass of the substance. This is how we calculate number of gram equivalents of the substance. How do you calculate moles? Given mass by molar mass. Given mass by molar mass is what you call as moles. Now, given mass by equivalent mass is what you call as number of gram equivalents. Right? Number one. Number two. Number of moles of the substance multiplied by n factor of substance. Number of moles of the substance multiplied by n factor of the substance. That gives me the number of gram equivalents of the substance. The third result. Normality of the solution multiplied by volume of solution in liters. Normality of the solution multiplied by volume of solution in liters. That gives me the gram equivalence of solute. That gives me the gram equivalence of solute. These three results I would want you guys to remember from now onwards to calculate what? To calculate gram equivalence of a substance. Similarly, in order to calculate the milli equivalence, if you are supposed to calculate milli equivalence of any substance, again I'm giving you three results. The first one, which you will remember directly, mass of substance in grams divided by equivalent mass of the substance multiplied with 1000. This gives you milli equivalence of the substance. Second result, instead of moles, I'll write number of millimoles. Number of millimoles of the substance multiplied by n factor of substance. The third result, normality of the solution multiplied by volume of solution in ml. That also gives me the milli equivalence of solute. So three results to calculate gram equivalence of any substance, three results to calculate milli equivalence of any substance. And do remember, number of milli equivalence of the substance is always equal to number of gram equivalence of the substance multiplied with 1000. These are the three things which I would want you guys to remember from now on. These are few results which I would want you guys to remember from now on. For example, understand. Let's say I'm writing one simple basic question. I'm writing, calculate the gram equivalence and milli equivalence in 31.6 grams of KMnO4 in acidic medium. Let's say this is the question. One simple question I wrote. I need to confirm the gram equivalence and milli equivalence which are present in 31.6 grams of KMnO4, right, in acidic medium. First of all, in acidic medium, what n factor KMnO4 shows? You should be remembering it now. N factor of KMnO4 in acidic medium is 5, right? Am I given with mass of KMnO4? Yes, this is my given mass of KMnO4. What am I supposed to calculate? Gram equivalence and milli equivalence. So I'll say number of gram equivalence of what? Number of gram equivalence of KMnO4 will be equal to given mass of KMnO4 in grams divided by equivalent mass of KMnO4. Given mass of KMnO4 is 31.6 grams divided by, what is the equivalent mass of KMnO4? Equivalent mass of KMnO4 will be molar mass of KMnO4 divided by n factor of KMnO4. When you solve it, the value comes out to be 1. The value comes out to be 1. Now what it means exactly? It means, my dear students, it's simple. It's pretty much simple. Now you can say something like this. You can say that we have got 31.6 grams of KMnO4, or you can say we have got 1 gram equivalent of KMnO4 in acidic medium. Both the things are similar. Both the things are same. Either you want to say that we have got 31.6 grams of KMnO4 in acidic medium, or you can say we have got 1 gram equivalent of KMnO4 in acidic medium. Both the things, they have got same significance. They have got same meaning. If you got the gram equivalence of KMnO4, you can easily calculate the number of milli equivalents of KMnO4 as well. It is going to be equal to the number of gram equivalents of KMnO4 multiplied by what? Multiplied by 1000. Correct? So 1 into 1000 comes out to be 1000 only. You can say we have got 1000 milli equivalents of KMnO4 here. The choice is all yours. Whatever you want to say, you can say that. If you want to say that we have got 31.6 grams of KMnO4, or you can say we have got 1 gram equivalent of KMnO4, or we have got 1000 milli equivalents of KMnO4 here. All the things are giving you the same meaning. I hope I'm clear with this. I hope I'm clear with this. Yeah? Right, people? Am I clear? All right. I hope you got to know, my dear students, the point is you have to remember these 3 results, right? Why these results you have to remember? Because these results I'll be directly using in titration. That's why I'm giving you these results. Okay? Now. There is something called as normality. Have you heard about the term normality before? You would have, right? Normality. Normality is represented by what? It's represented by capital N. Normality is represented by capital N. Normality is represented by capital N. How do we exactly define the term normality? Normality is defined as the number of gram equivalents. The number of gram equivalents. The number of gram equivalents of solute. Number of gram equivalents of solute which are present in 1 liter of solution. The number of gram equivalents of solute which are present in 1 liter of solution. That is something which you call as normality. For example, let's say you have got 1 liter of solution. If in 1 liter of solution there are 5 gram equivalents of solute. If in 1 liter of solution there are 5 gram equivalents of solute, you'll directly say normality of the solution is 5. If in 1 liter of solution there are 10 gram equivalents of solute, you'll say normality of solution is 10. If in 1 liter of solution there are x gram equivalents of solute, you'll directly say normality of the solution is x. So what is normality? It's nothing. Number of gram equivalents of solute which are present in 1 liter of solution. Now, how do you exactly calculate normality? Let me give you certain results. Normality is equal to number of gram equivalents of solute divided by volume of solution in liters. Number of gram equivalents of solute divided by volume of solution in liters. This is the first result with the help of which you calculate normality. Second result. Instead of gram equivalents of solute, I can write mass of solute in grams divided by equivalent mass of solute. Number of gram equivalents is given mass by equivalent mass. So, gram equivalents of solute, I can write mass of solute divided by equivalent mass of solute. And in the denominator, there is volume of solution in liters. I can write volume of solution in ml and I can multiply here with 1000. This becomes my one more result to calculate normality. Similarly, there is one more result to calculate normality, which is equal to molarity multiplied by n factor of solute. Molarity multiplied by n factor of solute. My dear students, these are 3 results which I would want you guys to remember to calculate what? To calculate normality of any solution. Gram equivalence of solute divided by volume of solution in liters. Mass of solute in grams multiplied by 1000. Equivalent mass of solute, volume of solution in ml. Molarity of the solution multiplied by n factor of solute. These are 3 results with the help of which we can calculate normality of the solution. Okay? 3 results with the help of which we can calculate normality of the solution. Now, let's try to understand a few more things. If you ask me, what is the unit of this normality? Units of normality. It's going to be simply gram equivalent per liter. Gram equivalent per liter. Or you can call it directly as normal. You can call it directly as normal. For example, sometimes if I write 2 normal if I write 2 normal NaCl aqueous solution, if I write 2 normal NaCl aqueous solution, what does it mean? What does it mean? It means that you have got solution whose normality is 2. It simply means that 2 gram equivalents of solute are present in 1 liter of solution. 2 gram equivalents of solute is present in 1 liter of solution. I believe I'm clear with this. I believe I'm clear with this, right? If I ask you, is normality temperature dependent or independent? What do you think? Since normality depends on volume, and volume depends on temperature, right? So your normality becomes temperature dependent concentration term, because normality is dependent on volume and volume itself is dependent on temperature. Okay? Right? So when will you teach chemical bonding? Do you want me to teach the chemical bonding the next chapter? Should it be the next chapter? If you want to, let me know afterwards in the comment section. Okay? If you want me to teach chemical bonding first, I can do that too. No issues. Yeah, is that? All right. Now, people, let me tell you, sometimes in the question, you'll find a term like this. Semi-normal solution. What is a semi-normal solution? What is a semi-normal solution? Semi-normal solution is the one whose normality is 0.5. Right? Sometimes they'll give you a term like this, deci-normal. Deci-normal solution is the one whose normality is 0.1. Sometimes they'll give you a term, centi-normal solution. Centi-normal solution. What is a centi-normal solution? The solution whose normality is 0.01. Sometimes they'll give a term that is millinormal solution. Millinormal solution is the one whose normality is 0.001. Okay, remember these terms as well. Sometimes just to confuse you, they can give you all this, right? Sometimes just to confuse you, they can give you all these terminologies. I hope this is clear. Now, if this is clear, let's try to solve one question so that you can understand this concept of normality. The question is, I'm giving you 0.1 molar HCl aqueous solution. Let me know what will be the normality of this solution. Quick. Till then, I'm going to write few more. 0.2 molar H2SO4 aqueous solution. Tell me about its normality. Tell me about its normality. For example, 0.3 molar H3PO2. Let's say 0.4 normal H3PO3. For example, 0.5 molar BOH thrice aqueous. Okay? Right? Tell me. Tell me, people. Over here, I want you to calculate normality. Over here, I want you to calculate molarity. Over here, I want you to calculate normality again. Can you solve this? I give you the result few minutes back only. Normality is equal to molarity multiplied by n factor. What is molarity here? 0.1. What about the n factor of HCl? It's 1. Value comes out be 0.1. Molarity is 0.2. N factor of H2SO4. 0.4. Normality is equal to molarity is 0.3. What is the N factor of H3PO2? An acid donates only that H positive which is attached to more electronegative element like oxygen. Now, in H3PO2, there is only one hydrogen which is attached to oxygen, so its N factor is 1. I hope you remember we have discussed this in detail. Similarly, molarity we have to calculate. Molarity will be normality divided by its N factor. What is its N factor? H3PO3. We have discussed its N factor. It is 2, that means 0.2. Normality is equal to molarity multiplied by boric acid. When you put boric acid into water, its N factor is, remember, N factor we have discussed. N factor of boric acid, that's 1. So 0.5. Okay? Perfect. I believe this is clear. Right? I believe this is clear. I believe this is clear. Now, similarly, guys, let me give you one more question so that you can understand properly. For example, the question is like this. Calculate the molarity and normality of a solution in which 63 grams of oxalic acid dihydrate are present in for example 500 ml of solution, 500 ml of aqueous solution. Can you solve this question on your own? You should be in a position to solve this question. As per this particular question is, guys, concerned, we are supposed to calculate molarity and normality. Now, in the question, they have mentioned one thing. 63 grams of what? Of oxalic acid dihydrate. What is oxalic acid dihydrate? It is your COH 2 times water, right? It will be basically C2H2O4. C2H2O4 dot 2 times water. This is your oxalic acid dihydrate. Now, 63 grams of oxalic acid dihydrate are present in 500 ml of solution, 500 ml of aqueous solution. Since the solution is aqueous, that means solvent is water. If water is solvent, that means this oxalic acid dihydrate becomes my solute, and this is the mass of solute. Mass of solute is generally represented by W2, which is 63 grams. What about the volume of the solution? Volume of the solution is given to me as 500 ml. What am I supposed to calculate? First, molarity. How do you get the molarity? Mass of solute in grams multiplied by 1000 divided by molar mass of solute and volume of solution in ml. This is the result with the help of which you can calculate molarity. You should know it. Yeah? Right, people? Now, what is W2 here? It is 63 multiplied by 1000 divided by. What is the molar mass of solute? Molar mass of this whole solute, when you calculate it, it will come out to be 126. Volume of solution in ml is 500. So this is 1, this is 2, right? Overall value comes out to be 1 only. So molarity of the solution is 1. My dear students, if you got the molarity, you can easily calculate normality as well. What is normality? Normality will be molarity multiplied by n factor of solute. Molarity is 1. N factor of this oxalic acid is 2. It can donate 2 H positives, right? So its normality is 2. Molarity is 1, normality is 2. These were the two things which I was supposed to calculate. Am I clear, people? Am I clear? Am I clear? Am I clear? There is just one topic that is left in the chapter, but that is super important topic. That is a super important topic. First of all, tell me till now if every single thing is clear or not. Quick. Part 2 of atomic structure will happen on Monday. Part 2 of atomic structure will be scheduled on Monday. Is it done? Is it done, people? All right. Let's move on then. Let's move on. And let's try to understand the law of chemical equivalence. The law of chemical equivalence. You call it as the equivalent concept as well. You call it as the equivalent concept as well. Equivalent concept, you'll be calling it as well. And this equivalent concept will be used where? Will be used this equivalent concept in the redox titration. We'll be using it in the redox titration. We'll be using it in redox titration. Okay, so we are going to enter into titration now. We are going to enter into titration now. See guys, look here. Look here. Let's try to understand what this equivalent concept is all about and how exactly we are going to use this equivalent concept in redox titration. Okay, there are a set of questions which I've come up with, which I'm going to show it to you, right? But before that, let's understand what this equivalence is all about. See guys, for example, you've got a reaction like this, A plus B. Let's say it gives C plus D. This is the reaction. A plus B gives C plus D. Is the reaction balanced? No, the reaction is not balanced. And in equivalent concept, we are not supposed to balance the reaction. That's the benefit of using the equivalent concept. That is the benefit of using the equivalent concept, right? So basically, I've got the reaction which is not balanced. A and B are reactants, C and D are products. Now, law of equivalence says that, it says that gram equivalence of A reacted in the reaction will be always equal to gram equivalence of B reacted, which will be equal to gram equivalence of C formed, which will be also equal to gram equivalence of D formed. As simple as that. If you have the reaction A plus B gives C plus D, where A and B are reactants, C and D are products, as per law of equivalence, whatever gram equivalence of A have reacted, same gram equivalence of B would have reacted, same gram equivalence of C would have formed, same gram equivalence of D would have formed. As simple as that. Since this particular statement I wrote in terms of gram equivalence, well, you can write this statement in terms of milli equivalence as well. You can say milli equivalence of A reacted will be always equal to milli equivalence of B reacted will be equal to milli equivalence of C formed will be equal to milli equivalence of D formed. Will be equal to milli equivalence of D formed. Well, this is the first concept, this is the first case from which we'll be getting the questions. It is just you have to write the statement. Milli equivalence of A has to be equal to milli equivalence of B equal to milli equivalence of C equal to milli equivalence of D. From this particular equation, we'll be getting one type of question. Now, the second case, then I'll show you the questions as well. I have got different sets of questions for you. But let me make you understand few things first of all. Case 2 here. My dear students, imagine you have taken a container, and in this container, for example, you have got a mixture of three things. Mixture of A, B, and C, for example. Let's say you have got a mixture of A, B, and C in the container. For example, you are adding D into this particular container. Let's say you are adding D into this particular container. You have got A plus B plus C in the container, mixture of A, B, C. Now you are introducing D here. For example, if I assume certain things, let's say if D reacts with A, B as well as C, then as per law of chemical equivalence, as per equivalent concept, I can say that gram equivalence of A reacted plus gram equivalence of B reacted plus gram equivalence of C reacted. It will be always equal to the gram equivalence of D reacted. Well, you wrote the statement in terms of gram equivalence. You could have written the statement in terms of milli equivalence as well. You could have mentioned it like this. Milli equivalence of A reacted plus milli equivalence of B reacted plus milli equivalence of C reacted. It has to be equal to what? It has to be equal to milli equivalence of D reacted. Okay? This is our first case here. In case of the mixtures. Now guys, over here try to understand one more thing. For example, if D is not reacting with all, if D reacts only with A and B, what will happen? If D reacts only with A and B, how do you write the statement? What law of equivalence says now? If D only reacts with A and B, then as per law of equivalence, I can say gram equivalence of A reacted plus gram equivalence of B reacted. It just will be equal to gram equivalence of D reacted. have got nothing to do with C over here. Or you can write the statement in terms of milli-equivalence. You can say milli-equivalence of A reacted plus milli-equivalence of B reacted. It has to be equal to what? Milli-equivalence of D reacted, right? From this particular slide, questions will be asked. Now, what kind of questions? Before showing you the questions, before showing you the variety of the questions, I would want you guys to remember certain n factors, which we have already discussed in the last session. In the last session, we have discussed certain n factors, and I would want you guys to remember those n factors. Okay, I would want you guys to remember those n factors. They are very important, right? First of all, this is something which you already will be knowing, KMnO4. What about the n factor of KMnO4 in acidic medium? 5. What about the n factor of K2Cr2O7 in acidic medium? 6. Now, for example, imagine that you have got FeSO4. You are making it to react with KMnO4 or K2Cr2O7. You are making it to react with KMnO4 or K2Cr2O7. What's going to happen? What's going to happen? You should know it now. Over here, you have got iron in di-positive state. And you know KMnO4 as well as K2Cr2O7 converts Fe di-positive into what? Into Fe tri-positive. KMnO4 as well as K2Cr2O7 converts this Fe di-positive here into Fe tri-positive. So what is the change in oxidation state? +2 to +3. Change is 1. 1 is the change for one atom. I have only 1. So n factor of FeSO4 over here in this reaction will be 1. So what I want you guys to remember, when KMnO4 and K2Cr2O7, when KMnO4 or K2Cr2O7 is treated with FeSO4 in acidic medium, you'll be taking the n factor of FeSO4 as 1. Okay, because Fe di-positive gets converted into Fe tri-positive there. Okay. Similarly, for example, you have got oxalate ion. Let's say you are treating oxalate with KMnO4 or K2Cr2O7. What happens? KMnO4 as well as K2Cr2O7 converts oxalate into carbon dioxide. Over here, the oxidation state of carbon is +3. And in carbon dioxide, it's +4. So +3 to +4, change is 1. 1 is the change for 1. I have 2. So its n factor here directly is 2. Similarly, if you have sodium oxalate, or for example, you have got potassium oxalate, and if they are treated with KMnO4 or K2Cr2O7 in acidic medium, you'll be taking their n factors directly as 2. You'll be taking their n factors directly as 2, right? For example, you have got ferrous oxalate, FeC2O4. If you are treating this ferrous oxalate into what? If you are treating this ferrous oxalate with KMnO4 or K2Cr2O7, what happens? If you are treating it with KMnO4 or K2Cr2O7 in acidic medium, what happens? Over here, iron is in +2 oxidation state, and this carbon is in +3. And we know KMnO4 converts Fe di-positive into Fe tri-positive, right? And KMnO4 converts oxalate into carbon dioxide. Perfect. So +2 to +3, increase in oxidation state. +3 to +4, increase in oxidation state. So can I say this is the species in which oxidation state of more than one element is increasing? And in the last session, I've told you, how do we calculate this n factor? It has to be n1 plus n2. And finally, it comes out to be 3. So remember it directly, it's 3. Remember it directly, it's 3. We have discussed it. We have discussed it. Right? Similarly, for example, you have got ferric oxalate, Fe2C2O4 whole thrice. When it's treated with KMnO4 or K2Cr2O7, since iron here is already in +3 oxidation state. Iron here is already in +3 oxidation state. So KMnO4 or K2Cr2O7 is going to do nothing with this Fe tri-positive. Right? Because KMnO4, K2Cr2O7 converts Fe di-positive into tri-positive. They do nothing with Fe tri-positive, right? KMnO4, K2Cr2O7, they do nothing with Fe tri-positive. Only thing, your KMnO4, K2Cr2O7, they are going to convert this oxalate ion into carbon dioxide. So +3 to +4, change is 1. 1 is the change for 1. I have 6. So its n factor, directly remember as 6. Similarly, you will see Cu2s, its n factor, remember as 8. Cus, in presence of your KMnO4, K2Cr2O7, its n factor will be 6. Okay. Similarly, you have got more salt. In more salt, Fe di-positive gets converted into Fe tri-positive when treated with KMnO4 or K2Cr2O7. So its n factor is directly 1. Similarly, H2O2 when treated with KMnO4, K2Cr2O7, its n factor is 2. See, these are some common n factors, guys, which you can remember. Right? Which you can remember. And if you can remember all these, then we are fit enough to solve the questions in very, very, very lesser time. Are you ready for the questions? Are you ready for the questions, guys? Are you ready for the questions here? Can you first of all tell me the answer of this question? Well, it's a simple question. This is not based on titration or something. It's a simple question. It's a simple question. Calculate the number of gram equivalents in 50 ml of 0.5 normal NaOH aqueous solution. So we are supposed to calculate milligram equivalents. So I'll say the number of gram equivalents of what? Of NaOH. Number of gram equivalents of NaOH. Now, how do we calculate the gram equivalents? There are three formulas if you remember. Formula based on mass, formula based on moles, formula based on normality. So it is normality multiplied by volume of solution in liters. Normality is how much? 0.5. Volume of solution is given to me as 50 ml, but I want in liters. So 50 divided by 1000. So this particular term is going to give you the number of gram equivalents of NaOH here. Okay, this is something which you know already. Now, I'm going on to the first question of the titration. First question of the titration. The question is pretty much simple. Just understand, look at the question carefully, and then we'll solve it. Then we'll solve the question. The question says what volume of 0.1 molar KMnO4 is required? What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium? Can you solve this? See guys, as far as this particular question is concerned, the question is saying your KMnO4, you are treating this KMnO4 with FeC2O4. You are making these two to react in acidic medium. Let me call this as number 1. Let me call this as number 2. First of all, do you remember their n factors? Yes, its n factor is 5 and its n factor is how much? Its n factor is 3. The question says what volume of 0.1 molar KMnO4? What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar? 100 ml of 0.3 molar ferrous oxalate in acidic medium. What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium? This is the question. So basically, these two are supposed to react. These two are supposed to react. Now, these two are supposed to react. The first thing, guys, since you know molarity of KMnO4, you know n factor of KMnO4, and molarity multiplied by n factor, that gives me normality. So normality of KMnO4 will be this multiplied by this. So it will be 0.5. Normality of the second one will be molarity multiplied by n factor. This multiplied by this. So 0.3 into 3 comes out to be 0.9. Right? Now, I will be using the equivalent concept. I'll be using the equivalent concept. Okay? Since these two are going to react, so as per equivalent concept, gram equivalence of KMnO4 reacted has to be equal to gram equivalence of ferrous oxalate reacted. Or milli equivalence of KMnO4 reacted has to be equal to milli equivalence of ferrous oxalate reacted. Right? Now, should I be writing the statement in terms of gram equivalence or should I be writing the statement in terms of milli equivalence? You tell me. Since volume is given in ml and when volume is in ml, we use the term milli equivalence, right? So I'll directly say milli equivalence of KMnO4 reacted has to be equal to the milli equivalence of ferrous oxalate reacted. Right? Their milli equivalents are supposed to be same. Now, milli equivalence of KMnO4. How many formulas do we have to calculate milli equivalence? 3 formulas. Mass, millimoles, normality. Which one I'll use here? I'll write normality of 1 multiplied by volume of 1 in ml. Similarly, this is going to be normality of 2 multiplied by volume of 2 in ml. Now, all the things are in front of you. N1, 0.5. V1 to be calculated. N2, 0.9. V2, 100. When you solve this, V1 comes out to be 180 ml. Well, you should know the meaning of this 180 ml here. What is this 180 ml here? What is the meaning of this 180 ml? I'll say V1. We got the volume of KMnO4. That is 180 ml. So I can say 180 ml of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.3 molar ferrous oxalate in acidic medium. That was the question. Simple. Right? Right, people? So this was our first question. Going into the second question. Look at this. Well, as far as this particular question is concerned, look, it is a similar type of question. What volume of 0.1 molar KMnO4 is required to oxidize 100 ml of 0.2 molar FeSO4 in acidic medium? So in this particular question, if you look carefully, which two species are reacting here? I can say your KMnO4 is reacting with what? your KMnO4 is reacting with FeSO4. In which medium? In acidic medium. And over here, iron is dipositive, and KMnO4 is going to convert this Fe dipositive into Fe tripositive. So they are going to react basically, right? Let me call this as number 1. Let me call this as number 2. Do you remember their N factors? N factor of this is 5. N factor of this, I told you a few minutes back, that's 1. Okay. Now, what volume of 0.1 molar KMnO4? Its molarity is 0.1. Its volume is to be calculated. Is required to oxidize 100 ml of 0.2 molar. Its molarity is 0.2. Its volume is equal to 100 ml. Correct? Now, people, the first thing. Molarity multiplied by N factor, that is going to give me the normality. So the normality of first one is going to be this into this, that's 0.5. Normality of the second one is going to be this multiplied by this, that is going to be 0.2, right? Now, since these two are reacting, so as per equivalent concept, you can say gram equivalence of this reacted should be equal to gram equivalence of this reacted. Or you can use a statement in terms of milli equivalence, right? Now, since the volume is in ml, and when volume is given in ml, we use a statement in terms of milli equivalence, right? So you can say milli equivalence of first reacted has to be equal to milli equivalence of second reacted. Milli equivalence of first will be taken as N1 multiplied by V1 in ml, and milli equivalence of second is going to be N2 multiplied by V2 in ml. Now, N1 value is nothing but 0.5. V1 value is to be calculated. N2 value is 0.2. V2 is 100. So V1 comes out to be 40 ml, right? So I would say 40 ml of 0.1 molar KMnO4 is required. Oxidize 100 ml of 0.2 molar FeSO4 in which medium? In acidic medium. Right? In acidic medium. I hope I'm clear with this. This was type 1. Let's move on to one more type of the question. Look at this question, guys. Look at this question. The question is, how many moles of KMnO4 will be required to react completely with 1 mole of potassium oxalate in acidic medium? So basically, as per this particular question is concerned, your KMnO4 is reacting with what? You are making KMnO4 to react with potassium oxalate. Calling this as number 1, calling this as number 2, right? Since, do you remember their N factors now? N factor of KMnO4 in acidic medium is 5. N factor of potassium oxalate over here will be 2, right? It will be 2. How many moles of KMnO4? We are supposed to get the moles of KMnO4. Will be required to react completely with 1 mole of potassium oxalate. We need to get the value of N1. Now, my dear students, which concept you are going to use? Since they are going to react, if they have to react, what is the concept? You can say gram equivalence of 1 reacted should be equal to gram equivalence of 2 reacted. Or you can say milli equivalence of 1 reacted has to be equal to milli equivalence of 2 reacted. Now, the data is given in terms of moles. The data is not in terms of millimoles. The data is in terms of moles. If the data is in terms of moles, you can use the statement gram equivalence. If it was millimoles, then you would have used the statement as milli equivalence, right? So I'll write gram equivalence of 1 reacted has to be equal to gram equivalence of 2 reacted, right? Now, how many formulas do we have to calculate gram equivalence? 3 formulas: mass, moles, normality. Which one I'll use here? I'll use the formula for moles. I'll write moles of 1 multiplied by N factor of 1 is equal to moles of 2 multiplied by N factor of 2. Moles of 1 I need to calculate. N factor 1 is 5. This is 1 and this is 2. N1 value is 2 by 5. 2 by 5 means 0.4. So I would say I got to know that 0.4 moles of KMnO4 are required to oxidize 1 mole of potassium oxalate in which medium? In acidic medium. Now, it's not necessary that they'll ask you about the moles of KMnO4. They can ask you about the mass of KMnO4 as well. What mass of KMnO4 is required? Since you got moles, you can convert this into mass. Moles multiplied by the molar mass of KMnO4. That gives me the mass of KMnO4, right? Simple. I hope these sort of questions you will be able to solve easily from now on. If yes, let me know once in the chats, quick. If yes, let me know once in the chats, quick. Perfect, guys. Okay, can you solve this question on your own? Look at it. Look at it quickly. So as far as this particular question is concerned, your K2Cr2O7 is reacting with what? It is reacting with Cu2s in acidic medium. Do you remember their n factors now? Its n factor is 6. Its n factor is 8. How many moles of this? I need to calculate its moles. Are required to react completely with 2.5 moles. We are given with its 2.5 moles. So just use the equivalent concept. Gram equivalence of this reacted has to be equal to gram equivalence of this reacted. Simple. Or milli equivalence of this is equal to milli equivalence of this. Now, since the data is in terms of moles, that's why I'm using the statement gram equivalence, right? So gram equivalence of first one means moles of 1 multiplied by n factor 1 is equal. This will be moles of 2 multiplied by n factor 2. Now, moles of 1, I need to calculate. N factor 1 is 6. Moles of 2 is 2.5. N factor 2 is 8. So, N1 here will be this multiplied by this divided by 6. 8540, right? It will be 200 by 6. Sorry, it will be 20 divided by 6. 20 by 6 means 10 by 3. 10 by 3 means 3.33. Right? So, N1 is 3.33. Clear? Simple? This is something which you are supposed to get. Okay, I hope this is clear. For example, let's say you have got a question like this. Let's say you've got a question like this. You should be able to solve this one as well. And it's pretty much simple. The question is 6 moles of An positive. 6 moles of An positive requires 2 moles of Cr2O7 dinegative. Requires 2 moles of Cr2O7 dinegative. For the oxidation of An positive into what? For the oxidation of An positive into AO3 negative in acidic medium. The value of N will be, you have to get this value, the charge present on A. This is the question. You have to get the charge present on A. Try to understand. Cr2O7 is converting An positive into AO3 negative, and in acidic medium, you should know it now, Cr2O7 dinegative itself will get converted into Cr tripositive. Okay? In acidic medium, we have discussed this. Now, guys, understand. If I ask you, let's call this as N1 first of all. Let's call this as N2. Now, if I ask you, what about the N factor of 1? What about the N factor of An positive? What about the N factor of An positive? Its oxidation state here is plus N. Its oxidation state of A here will be plus 5. So, plus N to plus 5. Changes, final minus initial ka mod. Final minus initial ka mod. This is the change in the oxidation state for one atom of A. I've got only one atom, so this is N factor. Now, what about the N factor of this Cr2O7 dinegative? This is plus 6 here. This is plus 3 here. Plus 6 to plus 3. The change is 3. 3 is the change for one atom. I have 2, so 3 2s are 6. Okay, I got their N factors. Since I got their N factors, now, since these two are reacting, if these two are reacting, I can use the equivalent concept. I can say gram equivalence of this reacted has to be equal to gram equivalence of this reacted, right? I can use the equivalent concept. Gram equivalence of An positive reacted should be equal to gram equivalence of this. Now, gram equivalence of An positive will be equal to N1 multiplied by N factor 1. Gram equivalence of this will be N2 multiplied by N factor 2, right? What is N1? 6. What is N factor 1? 5 minus N. What is N2? 2. What is N factor 2? That is 6. So, 6 cancelled. N value comes out to be 3. So, what is this N? This N was the charge present on A. So, the charge present on A over here is plus 3. So, A is going from plus 3 to plus 5 here. A is going from plus 3 to plus 5 here. Am I clear? Am I clear, people? This is one more type of question. Or, for example, let's say I am framing a question myself. The question is, for example, like this. Calculate the moles of KMnO4 required to oxidize. Calculate the moles of KMnO4 required to oxidize a mixture containing 1 mole each of FeSO4, FeC2O4 and Fe2SO4 whole thrice. In which medium? In acidic medium. In acidic medium. This is the question now. Look at the question carefully. Quickly, guys. Look at the question carefully. The question is based on case 2 that I gave you in equivalent concept. It is based on case 2. And what was the case 2? See, as far as the question is concerned, imagine this is the container which we have. And in this container, what all things are present? As per the question, in this container, you have got FeSO4. With FeSO4, you have got FeC2O4. And with C2O4, you have got Fe2SO4 twice, right? You have got 1 mole of each of them present. So, number of moles of this is 1. Number of moles of this is also 1 here. Number of moles of this is also 1. Now, what you are doing, you are introducing KMnO4 here. You need to calculate how many moles of KMnO4 are required to react with a mixture containing 1 mole of each here in acidic medium. First of all, the KMnO4 which you are introducing here, you need to check with what all substances the KMnO4 is going to react. Is KMnO4 going to react with this? Is KMnO4 going to react with this? Is KMnO4 going to react with this? Can you let me know in the chats with what KMnO4 is going to react with? See, first of all, here iron is in dipositive state and KMnO4, you know, that converts Fe dipositive into Fe tripositive. So, KMnO4 is going to react with this one. Yes. Ferrous oxalate. Fe dipositive, it will convert into tripositive. Oxalate into carbon dioxide. Yes, it's reacting with this one as well. But if you look at this species, here iron is in +3 oxidation state. Have you seen KMnO4 reacting with Fe tripositive? No. No, right? Sulfur here is in +6 oxidation state. Since KMnO4 is the oxidizing agent, it oxidizes others. It oxidizes others. Here, sulfur is in +6, which is the maximum oxidation state of sulfur. So sulfur cannot increase its oxidation state beyond +6, right? So this part cannot undergo oxidation here. So KMnO4 cannot oxidize this part as well, right? So in short, KMnO4 is not reacting with this overall species. Neither reacting with iron part, neither reacting with sulfate part. Okay? Now you got to know your KMnO4 is only reacting with this one and this one. So equivalent concept says that gram equivalence of 1 reacted, gram equivalence of 1 reacted plus gram equivalence of 2 reacted, it has to be equal to gram equivalence of 4 reacted. Right? Nothing to do with this one. I hope I'm clear with this concept. Yeah? Now, people, what is the N factor of FeSO4 here? It will be 1. What is the N factor of ferrous oxalate? It will be 3. What is the N factor of KMnO4 in acidic medium? It's 5. Right? Now use the formula. Gram equivalence of 1 is N1 multiplied by N factor 1 plus this will be N2 multiplied by N factor 2 is equal to N4 multiplied by N factor 4. For third, we have got nothing to do with third. This is 1 multiplied by 1. This multiplied with this, that's 1 plus N2 multiplied by N factor 2. 3 multiplied by 1 is 3 is equal to it's N4 multiplied by 5. So 3 plus 1 is 4. 4 by 5 is the answer. So N4 here came out to be 4 divided by 5, which comes out to be 0.8. So 0.8 moles of KMnO4 are required to oxidize a mixture containing 1 mole each. I hope this is also clear. I hope this is also clear to everyone. Yeah? This sort of a question you should be able to solve now. Atomic structure part 1 I have taken. There is one more part remaining which I'll be taking on Monday. Monday 7 p.m. It's going to be atomic structure part 2. Okay? I'll make the session public right now once this particular session ends. Guys, will you be able to solve this sort of a question now? Is it clear? Is it clear to you? Yeah? I hope this is clear. I hope this is clear. I hope this is clear. Look at this question. Look at this question, guys. Look at this question. 0.4 grams of a mixture containing sodium oxalate and potassium oxalate requires 50 ml of 1 by 60 molar K2Cr2O7 in acidic medium for the complete reaction. The mass of sodium oxalate is. The mass of sodium oxalate is. Understand what this question is. Well, you can expect this sort of a question also in the examination, right? You can expect this sort of a question as well. But it is just the calculation part is going to be easy, right? Concept-wise, it's going to be same. See guys, as far as this particular question is concerned, understand you've got a container, for example, and that container contains sodium oxalate and potassium oxalate. This is Na2C2O4 and you've got K2C2O4 as well. Sodium oxalate and potassium oxalate is there in the container. Okay. Now, 0.4 grams mixture of this. So the mass of entire mixture is 0.4 grams. The mass of this whole mixture is 0.4 grams. Okay. Mass of this whole mixture is 0.4 grams. Now, let me represent sodium oxalate by number 1. Let me represent potassium oxalate by number 2. Just to make calculations a bit easy. A bit easy. So, you've got 0.4 grams of a mixture containing sodium oxalate and potassium oxalate. Now, in this mixture, what are we adding? We are adding what? We are adding K2Cr2O7. We are adding K2Cr2O7. As per the question, molarity of K2Cr2O7 is 1 by 60 and volume of this K2Cr2O7 is 50 ml. So we are adding 50 ml of 1 by 60 molar K2Cr2O7 in the container, right? What do we need to calculate? We need to calculate the mass of sodium oxalate and the mass of potassium oxalate in the mixture. Divyashri, that's what I'm telling. There is only one part of atomic structure which I've already taught. Part 2, I'll be teaching on Monday 7 p.m. That will be live session. Okay. I hope I'm clear to you. Alright guys, so 0.4 grams of a mixture is there in the container. Now you're adding K2Cr2O7 into it. We need to calculate the mass of sodium oxalate and potassium oxalate in the mixture. So first of all, is this 0.4 grams? Is this the mass of entire mixture? Yes, this is the mass of entire mixture. Let's assume out of 0.4 grams, let the mass of sodium oxalate here be x grams. Therefore, mass of potassium oxalate will be 0.4 minus x grams, right? Let the mass of sodium oxalate is x grams here. So mass of potassium oxalate will be 0.4 minus x grams, right? By the way, what will be the n factor of sodium oxalate here? N factor of sodium oxalate is 2. N factor of potassium oxalate is also 2, correct? Now the K2Cr2O7 which you are adding here, it is going to react with this one as well as this one. Because this one carries oxalate, this one also contains oxalate. And K2Cr2O7 in acidic medium, it's going to convert oxalate into carbon dioxide, this oxalate into carbon dioxide as well. So the K2Cr2O7, which you are adding in the container, the K2Cr2O7 which you are adding in the container, it's going to react with both. It's going to react with both. Okay. So what is the concept which I'll be using here? If K2Cr2O7 which you're adding, if it is reacting with both, if you use the equivalent concept here, you can say gram equivalence of this reacted plus gram equivalence of this reacted should be equal to gram equivalence of K2Cr2O7 reacted, right? Or you can write the statement in terms of milli equivalence. Milli equivalence of this reacted plus milli equivalence of this reacted has to be equal to milli equivalence of that one reacted. Now, which statement should I use? Since volume is in ml, if volume is in ml, I'll prefer to write the statement of milli equivalence. I'll write milli equivalence of 1 reacted plus milli equivalence of 2 reacted has to be equal to milli equivalence of K2Cr2O7 reacted. That means milli equivalence of 3 reacted. Let me call this as 3. Let me call this as 3, right? Now guys, first of all, do you remember the n factor of K2Cr2O7? N factor of K2Cr2O7 is 6. Molarity is 1 by 60, n factor is 6. So 1 by 60 into 6 comes out to be 1 by 10. So normality of K2Cr2O7 is 1 by 10. Nothing more than that. This is the normality of K2Cr2O7. Now guys, milli equivalence of 1. Since 1 is your sodium oxalate, you just know its mass. You just have its mass, x grams. So instead of milli equivalence of sodium oxalate, I'll write mass of sodium oxalate divided by equivalent mass of sodium oxalate, which will be molar mass of sodium oxalate divided by n factor of sodium oxalate multiplied by 10 raised power 3. These are the milli equivalence of sodium oxalate plus milli equivalence of potassium oxalate will be equal to mass of potassium oxalate, which is 0.496 divided by equivalent mass of potassium oxalate, which is Molar mass of potassium oxalate divided by n factor of potassium oxalate multiplied by 10 raised power 3, right? Has to be equal to milli equivalence of 3, milli equivalence of K2Cr2O7, right? Since we know its normality, we know its volume. So its milli equivalence has to be equal to its normality, which is 1 by 10, multiplied by its volume in ml, which is 50. Now guys, look at this particular equation. And when you look at this particular equation, there is only one unknown. What is unknown? Unknown is x here. When you solve this equation, you can easily get the value of x here. And what is x? X is nothing but it is the mass of sodium oxalate in the mixture, right? It is the mass of sodium oxalate in the mixture. And once you get x, 0.496, that's going to give you the mass of potassium oxalate in the mixture as well, which is something I was supposed to calculate. Okay? Which is something I was supposed to calculate. I hope I'm clear with all these things. Okay? Perfect, guys, still here? All clear till here? Say it once in the chats quick. All clear till here? Now, there is just one type of question which I need to show you. That's all. We are done with Redox. One more type of question I would want to show you here. But before that, tell me whether all the things are clear or not. Yeah? Perfect? All right, people. Now, take a note of one statement. Just take a note of one statement. My dear students, if I'm writing something like this, equivalent mass of a compound, let's say the compound is AXBY. Let's say the compound is AXBY. Let's say the compound is AXBY. And this compound contains two elements, A and B. Let me tell you, equivalent mass of the compound is always equal to the sum of the equivalent masses of its elements. Remember it, right? For example, you have got magnesium oxide. Equivalent mass of magnesium oxide will be equal to equivalent mass of magnesium plus equivalent mass of oxygen. That's what I wrote over here. That's what I wrote over here. Equivalent mass of a compound AXBY will be equal to equivalent mass of A plus equivalent mass of B, right? Okay. For example, if I'm writing something like this, equivalent mass of metal oxide. Equivalent mass of metal oxide will be simply equal to equivalent mass of metal plus equivalent mass of oxygen. What is the equivalent mass of oxygen? It is 8. Equivalent mass of metal chloride, for example. You can write it directly as equivalent mass of metal plus equivalent mass of chlorine, which is 35.5. For example, equivalent mass of metal sulfate. Equivalent mass of metal sulfate will be equal to equivalent mass of metal plus equivalent mass of sulfate ion. Plus equivalent mass of sulfate ion, which will be equal to molar mass of SO4, that is 96, divided by its n factor, that is 2. So 96 divided by 2 is 48. So you can just write 48. Similarly, for example, if I write equivalent mass of metal nitrate, equivalent mass of metal nitrate will be equal to equivalent mass of metal plus equivalent mass of NO3 negative, right? Equivalent mass of NO3 negative will be equal to molar mass of NO3 divided by its n factor, that's 1. So 62 divided by 1 comes out to be 62. So this can be written like this. Okay, so first of all, I would want you guys to remember this particular scenario which I mentioned over here. This is important. Why it's important? Because I need to solve one specific type of the question here. I need to solve one specific type of the question here. Okay. So for example, I'm writing certain questions here. Let me see whether you can solve this or not. The question is like this. You might have seen these questions in modules as well. 1 gram of metal oxide. 1 gram of metal oxide gives 0.2 grams of metal. Gives 0.2 grams of metal. Calculate the equivalent mass of the metal. A very simple and basic question. 1 gram of metal oxide gives 0.2 grams of the metal. Calculate equivalent mass of the metal. Whenever you see this sort of equation, how do you approach it? See guys, you have got 1 gram of metal oxide. Let's say this is your metal oxide and you have taken its 1 gram. 1 gram of metal oxide gives what? It gives 0.2 grams of the metal. This is something which is given to me. 1 gram of metal oxide gives 0.2 grams of 1 gram of metal oxide gives 0.2 grams of metal. Calculate the equivalent mass of metal, right? Well, first of all, You know, in equivalent concept, am I supposed to balance the reaction or something? No, nothing like that. Now, people, if you use the equivalent concept, you can simply say gram equivalence of metal oxide reacted has to be equal to gram equivalence of metal formed. So gram equivalence of this and gram equivalence of this, they should be equal as per equivalent concept. Now, gram equivalence of metal oxide will be equal to mass of metal oxide divided by equivalent mass of metal oxide is equal to gram equivalence of metal will be mass of metal divided by equivalent mass of metal. Now, what is the mass of metal oxide? It's 1 gram. It's 1 gram divided by equivalent mass of metal oxide will be equivalent mass of metal plus equivalent mass of oxygen, which is 8, is equal. Mass of metal is nothing, 0.2 divided by equivalent mass of metal. Now just cross multiple here and get the equivalent mass of metal, and I believe it comes out to be 2 grams. Right? This is something I was supposed to calculate. Done and dusted. Am I clear with this? Am I clear with this? For example, you have got a question like this. Let's say you have got a question like this. 3 grams of a metal chloride. 3 grams of a metal chloride gives 2 grams of metal. Gives 2 grams of metal. Calculate equivalent mass of the metal. Calculate equivalent mass of the metal. Well, you should be able to solve this one as well. Well, as far as this particular question is concerned, you have got 3 grams of what? You have got 3 grams of metal chloride. And it's giving us what? It's giving us 2 grams of metal. We need to calculate equivalent mass of metal. Which concept I'll be using? Again, I'll be using the equivalent concept. I'll say gram equivalence of this. Gram equivalence of metal chloride, it has to be equal to the gram equivalence of metal. Now, gram equivalence of metal chloride will be equal to mass of metal chloride, which is 3 grams, divided by equivalent mass of metal chloride. Equivalent mass of metal chloride can be written as equivalent mass of metal plus equivalent mass of chlorine, 35.5, is equal to gram equivalence of metal is mass of metal divided by equivalent mass of metal. Just cross multiple and get the equivalent mass of metal here, which comes out to be, I think, 71 grams. This is something which I was supposed to calculate. Right? Did you understand? How am I solving these questions? Let me give you one more question. One more question, and after that, I'll be giving you one homework. 3 grams of metal oxide. 3 grams of metal oxide is completely converted to 5 grams of its chloride. Is completely converted to 5 grams of its chloride. Calculate the equivalent mass of metal. Calculate the equivalent mass of metal. How you are going to solve this? The question is similar. Just read the question carefully. The question is 3 grams. 3 grams of what? The question is 3 grams of metal oxide. 3 grams of metal oxide is completely converted to 5 grams. Is completely converted to 5 grams of its chloride. So I had metal oxide. Now this metal oxide is getting converted into metal chloride as per the question. Okay? Calculate the equivalent mass of metal. So just equate their equivalence. I can say gram equivalence of metal oxide has to be equal to what? It has to be equal to gram equivalence of metal chloride. Right? This is the concept which we use. Now, gram equivalence of metal oxide will be simply equal to mass of metal oxide divided by what? Divided by equivalent mass of metal oxide is equal. This is going to be mass of metal chloride divided by equivalent mass of metal chloride. Okay. Now, what is the mass of metal oxide? It is 3 grams. So 3 divided by equivalent mass of metal oxide is equivalent mass of metal plus equivalent mass of oxygen, which is 8. Mass of metal chloride. Mass of metal chloride is 5 divided by equivalent mass of metal chloride means equivalent mass of metal plus equivalent mass of chlorine, which is 35.5. Right? Just cross multiple things and get the equivalent mass of metal here. When you solve this, the value comes out to be 33.25 grams. This is something which you were supposed to calculate. I believe you can solve these sort of questions as well. Now, one last question that I'm giving you as the homework, and you guys will be letting me know the answer of that question in the comment section right after the video ends. Right? So the question is the 1 gram of metal nitrate gives 0.86 grams of metal sulfate. Calculate the equivalent mass of the metal. This is the question whose answer you will be telling me in the chats. Who is this nonsense completely spamming the chats? Did I block you right now? Okay, leave it. The session is almost over. So guys, this is your homework question. Do let me know its answer in the comment section of this particular video. So with this, we are done with a redox reaction. The redox reaction chapter is done and dusted. So with this chapter is completely done and dusted, right? Okay. Perfect, guys. Now I will be taking a session on Monday. On Monday, 7 p.m., it is going to be Atomic Structure Part 2. Atomic Structure Part 2, which is the final part of the chapter Atomic Structure, which is the last part of the chapter Atomic Structure. And on Monday, we'll be completing Atomic Structure as well. So I think, I'm not sure whether you guys have, just a second. Just a second, guys. The ones who have not watched the Atomic Structure Part 1, let me show you where you can check it. See, you can go to the video category, or just do one thing. Let's search here directly, Atomic Structure Part 1. Atomic Structure. Atomic Structure Part 1. Wasim sir. When you search it, yeah, this one. 3 weeks ago, I posted this video. The ones who have not watched it yet, okay, the ones who have not watched it yet, watch it before coming to the session. Okay, watch it before coming to the session. And I believe, yes, everything I have taught in detailed format here, right? Everything is detailed, completely detailed. Perfect. Do watch it. The video duration is 7 hours. So before coming to the Monday session, which is Atomic Structure Part 2, before coming into that, watch this completely, right? TPP of this chapter I'll share in the Telegram. Okay? No, on Monday it's going to be a live session. It will be a live session on Monday at 7 p.m. Perfect, but watch this particular session before coming to 7 p.m. Monday session. Okay, and I would want every one of you to join. Chalo, with this I'll be taking a leave then. I'll be sharing the PDF of this in the Telegram channel, which is Wasim Bhatt Chemistry Official, right? The ones who are not the part of it yet, join into the Telegram as soon as we are done. After atomic structure, we shall be starting, let's see, I don't know, chemical bonding or anything. Let's see. Hello guys, do let me know in the comment section of this video, okay, how you liked this.